That's probably useful for us.
You'd think, as long as you can figure out where to find it. All right, so 5-4 lesson. Okay, everybody got their notes out? Pencils in hand? Focused?
Probably that.
Okay, so 5-4 is graphing polynomial functions. Okay, so far we have graphed linear functions like 2 years ago. We did absolute value functions. You did quadratic functions. We did that in here. Okay, so, oh, and cubic. We just did that. So now we're going to keep going. And we're going to do quartics, quintics, so forth. Okay. Sound super hard?
Yeah. I think it's really easy. But it involves graphs.
Yeah. There you go.
Some people think rocket science is easy too, but it is.
Well, how about we go through it and then you can decide at the end of the lesson.
Sure.
Fair enough?
I'm gonna write all that down.
Maybe, yeah, I probably would write at least most of it down, yeah. Okay, so let's talk about the graphs of these functions, okay? These are functions that you know already, okay, at least so far. You know what f of x equals x looks like. What does x look like as a function? Uh-oh. What does the x look like as a function? Okay, it's linear. It has a slope of 1. It crosses right through the origin. It's a straight line. Looks like this. Y equals x.
Looks like what? Oh. Oh, I see that.
Oh, good. So, what is the domain of x? What are the x values that x can be? Anything, right? So, we can say the domain is from negative infinity to positive infinity. What are the range values? Range values are your y. So, what's the lowest one to the highest one? The same, right? Okay. What about the end behavior? Okay, so the end behavior is as x goes really, really far to the right, what is the y value doing? Where is it going? Going up to infinity.
Really far up.
Is that better?
Yeah, a little.
How about that? Here, maybe I can do this. Oh, that's too big. That's big, but then I lose my colors. Is that all right? Okay. As x approaches negative infinity, so as we go far to the left, what is the y value doing? Going down to what value? To negative infinity. Mm-hmm. Yes?
Could you send Nicole Gilbertson to the office for just a minute?
Sure. Okay. Everybody good with x?
No, wait, no.
Okay, let's talk about x squared. What does x squared look like? Okay, so we have a parabola. Everybody with me, or do I need to still wait for you?
I understand this. Weird, none of us.
Fallon knows, so there.
That's fine. How many students? Simulation.
Yeah. Okay, so x squared looks like what? A parabola. Ha, see, more than one student answered. Okay, so what is the domain? What are the values that x can be for a parabola? Okay, you're thinking y's. So domain is your x's. So left to right. Yes.
It will always be greater than set. Meaning it'll be greater than x.
You can put any number in. So the domain is going to be from negative infinity to positive infinity. Okay, there's no restriction on the x value. I can plug any number in and I will get something out. Okay, what about the range? What are the y values? What's the lowest y value to the highest y value? 0, okay? So in this case, it's going to be 0. So the bottom, that vertex spot, it's going to go from 0, and it's going to go up to infinity. Okay, what's my end behavior? As x approaches positive infinity, what's my y value doing? It's going to infinity. Okay, and as x approaches negative infinity, what's my y value doing? It's going where?
Negative.
That's that left side. What's that left side
positive.
going? Going up. Okay, so it's going up. They both go in the same direction.
For the range? I don't get that.
Because the range is your y values. Okay, so
why
this
0 though? What if it's going down?
because just x squared. Literally the function x squared.
Oh, it's not negative.
It's not negative x squared, just x squared.
Oh.
Okay, ready for x cubed? Okay, what does x cubed look like?
It's a John Travolta.
John Travolta, right? So we're looking at now a John Travolta with his right arm up and his left arm down. Okay. What is the domain of the John Travolta? What are the x values? Good. We can put any number in and we will get something out. Okay, what is my range? What's the lowest y value to the highest y value? Okay. What about my end behavior? As x approaches positive infinity, what's my y value doing? F of x approaches positive infinity. Okay, and if we look at the left side, what's the left hand going to? Negative infinity. Whoops. All right, here comes a new function. Are you ready? You feel like you've seen it before? You think it's one of the previous three? Oh, like which one? You want to make an educated guess? Oh. Okay, so x to the fourth. I'm going to put this into Desmos so you guys can see it. So we're looking at x to the fourth, and x to the fourth looks like a parabola.
But it's touching.
Okay, so if I compare this to x squared, no, it's only touching once. Okay, the difference between x squared and x to the fourth is that the x squared function is a little smoother. Okay, it has this nice smooth curvature, whereas the x to the fourth function is more rigid. Okay, still it only touches at 0, that red one. You see how even no matter how much I zoom in, it is increasing. It doesn't touch it more than once, but it just is more rigid. It looks flatter, so it increases slower than the x squared initially. Until you hit 1, and then it's going to increase faster. Okay, so bottom line here is that x to the fourth is simply a parabola. Okay, so what's my domain of a parabola? Negative infinity to positive infinity. And what's my range? What's the lowest y value to the highest? 0 to positive infinity. Okay, what about my end behavior? What is my right hand going to be doing? Going up. And what's my left hand doing? Also going up. Anybody happen to know what an x to the fifth function looks like?
Yeah,
A John
like
Travolta,
that.
but it's like weird.
No, like it's gonna be like kind of like
That
It's
one?
gonna go up slower.
Ah, okay. So let's graph it in Desmos. So x to the 5th looks like, what do you think that looks like? John Travolta. Okay, if we compare it to x to the 3rd, it's going to be very, very similar. But again, the higher the exponent, the more rigid it becomes. So it almost looks like squarish. What's that? Yeah, it exactly keeps flipping.
So the x to the 6th.
So, what? Say that louder. Okay, exactly. That's exactly right. Okay, so that's what you're supposed to conclude out of this here. If we have a function that has an even-powered exponent, what does it look like?
Parabola.
It's a parabola. If we have a function that has an odd exponent, what does it look like? A John Travolta. Okay, so the higher the exponent, the more rigid it becomes. So if I had something like x to the 100th, what would that look like? A parabola. And it would be so rigid that it would almost look like a box. Okay, but still it really does increase. And if you had x to the 101th, that would look like what? John Travolta. Very rigid, very boxy John Travolta. Okay. What's that?
I was like Minecraft character, John Travolta.
Yeah, exactly. Okay, so basically make sure that you understand that, or at least have it written in your notes, that even-powered functions have this information. Okay, so even-powered exponents, domain is from -infinity to +infinity, the range is 0 to infinity, and both hands are going up. Okay, and make sure for odds you have the stuff for an x cubic function right now. Okay, so am I okay to progress, or do I need to wait for people to keep writing? Good?
What about for the 5th one? Are we not gonna write the domain?
No, I'm not going to write it because it's going to be exactly the same as x cubed. Okay, so if you want to fill that in on yours. And x to the 6th would just be a parabola. Okay, so the next part of this is now they go through and talk about what happens if you throw a negative in front. Okay, do we need to go over this? If you put a negative in front of any function, what happens to it? Reflects over the x-axis. Okay, so it flips it upside down. So what does negative x look like? Yeah, okay, so the slope would go down like this. Okay, what does negative x squared look like? Upside down parabola, right? What does a negative x cubed look like?
Left hand going up.
Okay, the left hand goes up, yep. Okay, and so forth, right? Parabola.
Would the domain and range change?
So the domains will always be from -infinity to +infinity. The only thing that changes is the range on the parabolas. Because now, since it's upside down, it's going to go from -infinity to 0. Okay? The end behavior on all of them just flips. Right? Do we need to talk about the end behavior on each of those? Just flips. It just flips, right? You guys understand what that is and how you can come up with it, right? Okay. So, the next part of this is graphing these polynomials. And we're going to be graphing them within factored form, okay? So, it's going to take you through this idea, and hopefully you're going to start to notice things, okay? So, this is kind of cool. So, the first little piece of this is x cubed, okay? So, what does x cubed look like? We just talked about this. X cubed. It's up to you if you want to write this or not. I would probably at least draw the graphs of these and talk about the pieces that are in it.
Print this out for us, multi. It's so hard. It takes so long. Yeah.
It's in my OneNote. I can print it at the end of class if you want. Okay, so x cubed looks like
It's a
x cubed. There we go. Hi guys. X cubed looks like a John Travolta with his right arm up, right? X cubed. Okay, can you guys see this, right? I want to be able to see the graph at the same time. Okay, so how many distinct factors does x cubed have? How many quantities are involved? How many terms are involved? One term. One term, one quantity. There's only one factor of this. Okay, where does it cross the x-axis?
0.
At 0, 0, so it crosses at 0. Okay, is the graph tangent? You guys remember what tangent means? We talked a little bit about it with parabolas. So the idea of a tangent line is something that bounces off of the x-axis. Okay, so does this function bounce off the x-axis like a parabola would? No. Okay, so no bouncing. Does it have a turning point? So a turning point is when it changes from going up to going down, or from going down to going up. Okay, yeah, same thing as the bounce. There's no turning points in this one. Do we have a maximum?
No.
No maximum. Goes to infinity. What about a minimum?
No.
No. Okay. Next function. Okay, so can you see the next one? It says x squared times the quantity x minus 2. Okay, I'm going to graph this one in Desmos here so you can see what it looks like. So we have x squared, nope, squared, and x minus 2. Is that what it was? There it was. Okay, so what is that?
Scary.
That is a John Travolta. Okay, so that is a John Travolta that's got like a little bit more disco dancing going on. Okay, he is wiggling. He's cruising, okay? So, where does this one cross the x-axis?
0, 0, and 2.
At 0 and 2. Is there any way you could have figured that out without looking at the graph? How do we find x-intercepts? True, but how do we do it algebraically? Do you remember how you find x-intercepts? You're on the right track.
Outside and inside of the parentheses.
Okay, yeah, what do you do with the parentheses?
Well,
Set them equal to what number?
to that.
To 0. Remember that zeros, x-intercepts are also known as zeros? So if I took x squared and set it equal to 0, what would I get? 0. Boom. If I took x minus 2 and set that equal to 0, what would I get? 2. Okay. So, let me draw this.
If it was x cubed,
Mm-hmm.
would it still equal 0?
What do you mean still, would what still equal 0?
The x axis.
X cubed? Yeah.
Okay.
Yeah. See? This one right here, x cubed, it crosses at 0. X cubed equaling 0 is 0. 0 cubed is 0.
Oh yeah.
Okay, so how many factors do I have for the second column?
2.
How many? There's x squared and x minus 2, so there's 2. How many zeros did I get?
2.
2, right? So I got 1 at 0 and 1 at 2. Did I get any bouncing on this graph?
Yes.
Yes. Okay, so this one bounced. You guys see where the bounce was right there? Got 1 at 0. Interesting. Think about that 0, 1. We're going to come back to that idea. What's that? You can get a double bounce, absolutely. It's a possibility. We'll get there. Wait for it. Okay, do I have any turning points? How many turning points? 2. Okay, so turning point is basically like a maximum or a minimum. Okay, so I have 1 there and I have 1 there, so there's 2 turning points. How many maximums are there? Well, there's 1 max, right? So there's a little max right there, a little relative max. And then I have 1 relative min, right? Okay. Oh, they use the word local as opposed to relative. So yeah, so local. So there's a local max and one local min. Okay. All right, moving on to the next one. Are you ready? So the third one now is x times x minus 2 times x plus 2. Anybody want to make a guess as to what this looks like?
It's gonna look like the second one, but on top.
What do you mean? That's the second one on top. So are you saying it's looking like a John Travolta or a parabola?
Wait.
Parabola? John Travolta. Where does it cross the x-axis?
On the other side, on the other side.
There is one on the negative, so it's 0, 2, and negative 2, right? 0, 2, and negative 2.
So there's just gonna be three.
Three little, yeah, well, x minus 2 and x plus 2. Okay, so what is that? What shape is it?
That's two parabolas.
That's a John Travolta. That's a John Travolta with a wiggle. It's got his right arm up, it's got his left arm down. But he's got, again, some wiggling going on. Okay, so and you see those three x-intercepts? We got one at negative 2, we got one at 0, and we got one at positive 2.
So x is just gonna equal 0.
Nope, not every time.
No, but for that.
Oh, when it's x? Yeah,
Or like x cubed.
sure, yeah.
X squared.
Mm-hmm.
X quadruple.
Okay, so this one looked like this. Whoa, I totally missed that.
Is that good, bro? Just check.
So how many factors did we have for the third one?
3.
3, which resulted in how many zeros?
3.
3 zeros. So the zeros were negative 2, 0, and 2. Did I have any bouncing?
Yes.
You did? You saw bouncing? Bouncing off the x-axis.
Oh.
Yes.
Yes. Yes.
Does it bounce off the x-axis?
Use the bucket. It goes.
A bounce goes, touches the x-axis and bounces off. Like think of a ball, like if it was going to hit the x-axis and bounce.
Yeah.
Does it bounce off the x-axis?
No.
Yeah.
Yes, on the bottom one.
No. There's no bouncing off the x-axis.
Oh, wait, it's bouncing off this one.
Here, let me graph the other one.
I'm so confused. It goes up.
Okay, so the black one has a bounce. You see how the black one has a bounce? That's a bounce.
Okay.
Okay.
Oh, so it has to start like that.
Right. Okay, so we have no bouncing. Do we have any turning points? Is there a max or min? Look right here, right here. Okay, we have 2 turning points. There's one right there and one right there. 2. Okay, so we have a local max, one local max, and we have one local min. Local, not global. So, have we figured out what makes a John Travolta yet?
Yeah.
What? Well, we know that's what is a John Travolta, but what if I just threw out some random function, would you know that it looked like a John Travolta?
No.
Okay, let's try these ones.
The x doesn't have an x.
Kinda. Okay, so x to the 4th.
That's parabola.
They're all parabolas.
Okay, x to the 4th is a parabola.
But they look weird.
It's one distinct.
A rigid parabola. Okay, so there's one factor for x to the 4th. What's my x-intercept?
0, 0.
0. Is there bouncing?
Yes.
Yes, there is a bounce. Do I have a turning point?
Yes.
Yes. One turning point. Oops.
You only have a min.
How many? And I only have a min, so there's no global max, but there is a global. Whoops, I can't spell global. Global.
I don't get that. It's local. Why is it global? Global is like through the entire graph, and local is in just one
Right,
area.
right. So there, global means it is the lowest place
It should be heavy.
of the entire graph. Local means it goes up and then it comes back down, but there's another spot that exists lower than it.
So if it was just like the John Travolta, would that be global?
Local. John Travolta's are local. Because the hands go further. Parabolas will have local.
What?
Or, no, sorry, global. You're right, sorry, my bad.
Okay. I was like, wait. Hey, those, it should be called hemisphere. I mean,
The shape of it? Okay. Alright, what about this function right here? X cubed times x minus 2. Anybody want to dare to venture what that might look like?
Yes,
It's
two.
parabola.
You're going to the left, right two.
it's a really rigid.
Okay.
Oh my gosh, no, you're not.
It's just making it bigger, like the one we already saw.
It's a John Travolta to the right.
A John Travolta to the right.
That is right.
That is my final answer. Okay, let's see.
What is it? X cubed?
X to the third.
Quantity X.
X to the third, and the quantity was x minus 2.
What the hell?
What
is this? I don't like this. That's not gonna happen.
Maybe it's.
Okay, so by definition, this is not exactly a parabola, but it's parabolic in nature. It has end behavior going up. Okay, but it's like a funky parabola where we got a lot more happening.
It's more on the hung out.
It looks.
Okay, so for this one, if we talk about the features of this one.
This is the most broken graph I've ever seen. Easy.
Looks something like that. So it's parabolic. How many factors did it have?
Oh my god, that's scary.
Or does it have?
2.
2. So what are the two x-intercepts?
0 and 0 and 2.
0 and 2. Did it bounce?
Yes. No.
No, it crossed. Does it have a turning point?
Yes.
How many?
3. 1.
1 turning point, because there's only a minimum. This right here, this still decreases the whole time. Decreasing, 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 decreasing. Now it goes increasing. So there's 1 turning point. Only 1 right there at the very bottom. Okay, so do I have any maximums?
Yes.
No. What about minimum?
Yes.
Yes. 1 global. What?
One global min.
Why not 3?
How do you see 3?
Minimum is like
The bottoms? How many of these do you see? 1. Alright, third one. Are you ready for this one?
This one's weird, though.
You guys already graphed it?
Yeah.
So what does it look like?
John Travolta.
No.
John Travolta?
Yeah.
So it was x squared, x minus 2, and x plus 2. Ready? What is this one?
W.
It does look like a W or a 2. Yeah.
Yeah, it's a little
Okay,
bit symmetrical.
so this one still has that parabola behavior, but again, there's weird wiggling going on below, okay? Do you see where it crosses the x-axis?
Yeah.
-2, 0, and +2. Have you figured out when we find parabolas and when we find John Travoltas yet?
Wait, go on.
We're not at that level.
Ooh, that was a bad drawing. Okay, how many factors do we have?
3.
3? 0, -2, and +2. Did we have a bounce? Anybody figure out when bounces occur?
Yes.
What makes a graph bounce?
1.
When it hits that.
1 bounce. Yep, 1 bounce.
How many turning points?
How many turning points?
2. No. Oh, yeah.
3.
What the heck?
Look. Decreases, then increases. There's a turning point, there's a turning point, there's a turning point. How many maxes do I have? 1. 1, what kind? Local? Mins?
2.
2, what kinds?
Global.
2 globes. Interesting. They are global because they're the lowest place on the entire graph. It does not go lower than that. Okay, ready for the last one? Anybody want to guess what this looks like?
I don't want to think it's 4 x's, so it's parabolas.
Wait. Say that again.
There's 4 x's, so it's x to the 4th, meaning it's a parabola. Right? It's probably like probably scary parabola.
Okay, that was a really good observation. How many x's are there? Okay, do you see my function up here? X minus 2, x plus 2, x minus 3. How many x's are there? 4.
Oh my gosh, I see that.
X to the 4th. What does it look like? It looks like a parabola with some funkiness, right?
Wait, can you go up like really fast?
Go up.
Up really fast.
Hold on, let me put this in. X minus 2. What was it? X plus 2. And x plus 3. Thank you. Okay, so look at this one. Oh my gosh.
Wow, that's whoa.
That is very asymmetrical.
Yeah. There's definitely no symmetry in there.
No symmetry.
No symmetry. But what does it look like? It's a parabola.
It's almost like it's almost. Look at it though. Hey, no, that's not John because it has Travolta. That kid out here. It has 2 of them.
If I zoom super far out, it looks parabolic. Look. There's a parabola. Glad we agree.
Wait, go back to the other thing. And then to the other chart. I just want to see something like that. Oh, what I do. Sorry. Oh, okay. 2, 3, 4, 2, 3. For the x's on that one, it's on.
There's 3, right? So those all look like John Travolta's. Okay. So this one went like what did it go? Something like that. Okay, so we had 4 factors. We had how many x-intercepts? 4, right? So we had 0, 2, -2, and -3. Did we have a bounce?
No.
No bouncing. No bouncing on the trampoline. Assuming the trampoline is the x-axis. Turning points? How many turning points?
3.
3 turning points. Any maxes? 1 max. 1 local max.
2 global wins.
And actually there's 1 local and 1 global.
Why?
Okay, so the one that is, this one is a local. Because it's a minimum, but this one is lower than that. So this one is the global min, or min. Global min. See how this one up here, right here, that's a local. See, it's a minimum. It's the bottom of the graph. But this one is lower. So that's the global minimum. That's a local. Okay, so let's put this all together. Are you ready? Because we still haven't totally figured this out yet. I think for the most part you've kind of figured out what makes what, but you still haven't figured out when bouncing occurs. So I'm going to give you a very basic function and see if you can figure this out. Are we ready?
No. Yes.
Okay, so first of all, stop talking and listen. What does this look like? Why does it look like a John Travolta?
There's 5 x's.
There's 5 x's. Okay, now does everybody see the 5 x's?
Squared.
Okay, yep, there's 2 here and 3 there. So this is an x to the 5th. It looks like a John
That's a
Travolta.
lot of X's.
Where does it cross the x-axis?
3, -9. No, 3, 9.
So just set each of them equal to 0. There's only 2 x-intercepts. 3 and -4. Okay, so can you envision this? John Travolta, right arm up, left arm down, crosses through those 2 points. Ready? So we had x minus 3 squared and x plus 4 to the 3rd.
This is just making my brain.
What does this look like?
It's like a mountain thing.
It does look like an earthquake. Okay, so this looks like a John Travolta. For the end behavior, the right arm is up and the left arm is down. What happened at the 0 of -4? Did it cross or did it bounce? It crossed. What happened at the 3? Can you tell me when it bounces and when it crosses?
Bounces at negative and crosses at positive.
Doesn't have to do with positive or negative, no.
It's the exponent.
It has to do with the exponents. Okay, so you see these exponents right here? If you have an even exponent, that causes a bounce in the graph. If you have an odd exponent, it crosses through.
Oh, because, okay, so that makes sense because
What do you mean,
make
what do you mean?
parabola with even, right?
Yeah,
Evens makes a parabola. And,
Right.
Okay, odd makes.
so even exponent is a bounce. Odd exponent crosses. Write that in your notes. Okay, so we're looking right here. Okay, now for you to be drawing these, I'm not going to be analyzing how high your max and your mins are. Okay, so what you should be doing is you're going to draw these through, so it's going to have the bounce at which value, by the way? Which one is my bounce?
3.
The bounce is at the +3, so I'm going to cross through at 4, and you saw in the graph it kind of did this like John Travolta, you wiggle, and then it went up, and then it went back down. Whoops, good lord, let me try that way. Yeah.
That's just how I'm going to draw it.
Okay, so I'm not going to be looking at your max or mins. The only way for you to figure out how high and how low a function goes is by either using Desmos or a calculator, or by using calculus, which we're not going to do in this class. So, no, we won't do calculus in this class. Okay, do I need to go over an example of this that you will have to do, like this one? Everybody's okay with doing this?
No.
Can I do one really quick example? How about?
Yeah, it's okay.
Okay. What does this one look like? Negative what? No. How many x's are there? There's 3. So what does it look like? See, there's x squared and x. X. How many are in x squared? Okay. So this is going to look like a negative x cubed function. So what does it look like? John Travolta, which arm is up? Okay, so it goes like this, right?
How does she know? How do you know that?
Because it's a negative. It's flipped upside down. Okay, where does...
Which negative says that?
The very front negative. One in the front. Okay, where does it cross the x-axis? Guys, quit talking in the back. Jose, shh.
At 4.
Where does it cross the x-axis?
At like
Positive 4.
Look at the function. Look.
4.
Can you see that from here instead of there?
4.
Where does it cross? 0. Okay. And is it a bounce or does it cross at 0? Look. What did we just talk about with the exponents? If it's even, it bounces. So there's a bounce here.
I'm so now, how did it? It's on
0, 2. What? So it depends. This is even. So it also crosses at 4.
Oh,
Does it
okay.
cross or bounce?
It bounces. Or crosses. It's negative also. Oh, it's a positive. Oh, never mind, never mind.
Right. Well, it's an invisible 1. There's one of those quantities.
4 is not odd.
Okay, so to draw this, okay, I know my left arm is down, my right arm goes up. I know I'm going to bounce at 0, and I'm going to cross at -4. Okay, so if I go from left to right, I'm going to start with my arm up. I'm going to come down, bounce off to 0, go back up, and cross down through 4.
I'm so confused. Why is it cross through 4?
Are you worried about the 4 or the crossing?
The crossing.
What's the exponent that's right here?
negative plus.
1. Is 1 an odd number or an even number?
Oh. It's their exponent.
Even bounces, odd crosses.
Okay, that's
Okay, are we good?
doesn't matter where